In this presentation, I will discuss our paper Counting Active S-Boxes is Not Enough. This is joint work with Dunkelman, Abhishek Kumar, and Somitra Sanadhya, and I, Eran Lambooij, will present. This work is inspired by the works of Nieberg and Knudsen, as well as the design strategy of the ES, also named the Widetrail design strategy. Many designers use this design strategy to prove security bounds on the ciphers. In this work, we want to show that these bounds are not always accurate and things can go wrong in a very delicate manner. We show how a provable secure block cipher can still be distinguished from a random permutation. Thus, as the title says, counting active S-boxes is not enough. So, as this presentation is about symmetric cryptography, I will give a very quick refresher of block ciphers. So basically what you see here is a block cipher. There's a function E that takes as inputs a P and a K and outputs ciphertext C. Now, why is it called symmetric? Because the inverse of the function, D for decrypt, takes the same key and the ciphertext and produces the plaintext P. Now, what we will look at in this paper, or in this presentation paper, are distinguishers and how to bound the best possible distinguishers for a cipher. A distinguisher is basically an algorithm such that we distinguish the cipher from a random permutation. So the distinguisher that we will be looking at is the differential distinguisher introduced by Biam and Shamir in 1993, which basically looks at relationships between the input and the output difference. So the input difference would be a plaintext P XORed with some plaintext P prime, and then we follow the difference through the cipher, which we call a characteristic, and we'll get output difference C and C prime. And if the probability for such a characteristic is high enough, then we can use this to distinguish the cipher from a random permutation. Now, as I said in the introduction, we are looking at the Widetrail design strategy, and this is basically based on the work of Nieberg and Knudsen from 1995, which provided us with a framework to prove that the cipher is secure against differential cryptanalysis. So basically what they did, if we have a differential in a cipher which happens with a probability P, then we need at least 1 over P data, so inputs, input pairs with a certain input difference to be able to distinguish this, to see this property in the cipher. Now, if we have a cipher, a symmetric cipher, we also have a block size, and if we take that to be n, then we can only have at most 2 to the n input pairs with a certain input difference. Now, we can thus conclude that if the best differential, the probability for the best differential is smaller than 2 to the minus n, the cipher is secure against differential cryptanalysis. Now, so the work by Nieberg and Knudsen was the basis for the Widetrail design strategy that was also employed in the design of the AES. And what it does, it looks at what the Widetrail design strategy does is looking at the construction of the cipher, and it tries to bound the probability of the best differential characteristic. To do this, we split the cipher into linear and non-linear parts, and as usual, we will take the non-linear components to be S-boxes. So from now on, I will say S-box and non-linear components a bit interchangeably. We then compute, we can compute the maximum differential probability through an active S-box. And then if we count the minimum number of active S-boxes in a characteristic, in any characteristic of R rounds, and we can compute a lower bound for any characteristic of R bound. So a lower bound on the probability, of course. And this we can, of course, also use to compute the minimum number of rounds that we need for the security level that we want. As a side note, as most of you probably know, this is used by a lot of designers to as a very convenient tool to approximate the strength of the cipher against certain attacks, such as differential and also linear cryptanalysis. There are some assumptions being made, and those assumptions, as we will see later, can have actually a bad effect on the security. So you won't get the security that you hoped for. And to show this, I will introduce two ciphers that are very related to each other, and they will show the problems that you get when only relying on the Widetrail design strategy in the analysis of a new cipher. So, as I said before, we will be looking at two ciphers, but they're very related. So both of the ciphers will have a 128-bit block and use the AES S-box for the nonlinear layer, which is called here the S layer. And we'll have a permutation layer P, which basically is an MDS matrix, an 8x8 MDS matrix. So what we will have here is we have a 128-bit input that we split into two. So it's a Feistel construction here. And we have some 64-bit round key that we don't really care about, just take some uniform random value for that. And then we compute the S-box, like 8 S-boxes in parallel, and we combine those with a MDS matrix P. This cipher has 16 rounds, and as we will show in the next slides, if we follow the Widetrail design strategy, this is plenty enough to be secure against this differential cryptanalysis. It's actually, it is secure enough against differential cryptanalysis. And we computed the minimum number of active S-boxes for this cipher using MLP for R rounds and R between 1 and 16, of course. So if you look at this table that depicts the number of active S-boxes for the number of rounds, we see that at round 11, we have 22 active S-boxes. And if we recall that the AES S-box has a maximum differential probability of 2 to the minus 6, we can compute that then the probability, the best probability of a characteristic is 2 to the minus 132. If we look at 16 rounds, so that's already at 11 rounds, it's plenty good enough if you look at characteristics. And if we go to 16 rounds, then we see that 39 active, that we at least have 39 active S-boxes for the best characteristic. And this will give us a probability of 2 to the minus 234, which of course is more than enough for 128-bit block size. Now we'll move to the second cipher, and we can see here that what we basically did was squish 4 rounds or 4 of these SP layers into 1 round. And we did that to reduce the number of rounds. And to keep the resources the same as the previous cipher, and as we will see, the security is also quite similar to the previous cipher. We only have 4 rounds in this construction. but we will have the same number of SP layers. So as we will see, the security won't be much worse. Like there are 3 active S boxes less, but that doesn't really matter too much. Now, to compute the number of active S boxes, we take a slightly different approach than for the first cipher, because it's easier here to do. Because we know that P is an MDS matrix, and we also know that if we have 2 consecutive SP layers, we need to have at least 9 active S boxes if the input to the SP layers is of course active. And since we have 4 consecutive SP layers, we will need at least 18 active S boxes in one round, in one active round. And that means that the input to the round is non-zero. Now, we know that for a Feistel network of 4 rounds, we have at least 2 active rounds in differential cryptanalysis. So that will give us for the 4 rounds at least 36 active S boxes. And this gives us a lower bound on the probability of the best differential characteristic of 2 to the minus 216. So again, this is plenty. But pools show that actually this analysis is not that accurate if we analyze it a bit more carefully. Okay, so let's have a look at a differential distinguisher on a 4-rhyme. It's Feistel network, and we see here that we have 2, as I said before, we have 2 rounds that are active, round 2 and 3. And if we have a 0 alpha input difference, we get a beta 0 output difference with probability P1 times P2, assuming that everything is independent of each other, of course, otherwise the probability will change. But we, as always, assume here that we have round independence. Now, what I want to do here is to look at the round functions as sort of black boxes for now, where F1 gets us the input, the round keys, and the input. So it's basically it's a 64-bit permutation given a set of round keys. So that if we can compute a DDT for F1, F2, F3, F4, and of course only for F2 and F3, this is useful, but the DDT for F2 and F3 are different, but we can say something about it. And if there is a large enough entry in the DDT of F2, which we will call DDT2, and a large enough entry in F3 that we call DDT3, then we can have a distinguisher. So what we need actually is in DDT2 a transition from alpha to beta with a high value, and in DDT3 a transition from beta to alpha with a high value. And if that happens, we have a differential distinguisher for the cipher, and thus also the cipher that we discussed before with the 4 rounds. Now, if we want to say something about the DDT, then we should look at how the distribution of the entries of the DDT behave. And luckily for us, O'Connor did that in '93 and came with this distribution. And now what is left to do is to compute if we can have this event that DDT2 alpha goes to beta with a high value, and beta goes to alpha with a high value in DDT3. And if we follow this distribution, then in each of the 64 rows, we have 8 entries of 32. Thus, with a high probability, we'll get DDT2 alpha goes to beta with a value of 32, and also with a high, and DDT3 beta goes to alpha with a value of 32. Now, Now, if we fill in these figures into the differential that we got before, we'll see that P1 turns into 32 times 2 to the minus 64 and P2 as well. So the probability of this differential now becomes 32 times 2 to the minus 64 squared, which gives us 2 to the minus 180, which is a lot lower than what we predicted with the Widetrail analysis before. So does this distinguish the cipher? For that, we need to first look at one other thing, because we need to distinguish it from a random permutation on 128 bits. And we know that this permutation, we can also create a DDT for that, or we can see the differential probability of going from input difference to a output difference in the DDT. And following O'Connor's work, again, we know that with high probability, the maximum value in this DDT for a random permutation will be 100. And this will give us a probability of approximately 2 to the minus 121 for any differential in the cipher. So we can conclude that this distinguisher is this cipher is distinguishable from a random permutation. So now the most important part: what went wrong here? Because clearly we are contradicting the proof that we gave with the Widetrail analysis that we did earlier. Now that's not entirely true, of course, but we'll come back to that later. So what we have is a differential distinguisher with the probability of 2 to the minus 118, while the Widetrail analysis gave us a probability for the best characteristic of 2 to the minus 216. And the problem here is the difference between the differentials and the characteristics, because a differential you can see as a set of differential characteristics that all go from one input difference to the same output difference, like to a output difference. And what the Widetrail design strategy does not account for is the existence of differentials. And this actually is one of the major pitfalls of using the Widetrail design strategy for the analysis of the cipher. So to conclude, I will repeat the title. Only counting active S boxes is not enough. Does this mean that we should not use the Widetrail design strategy? No, it is a very useful and powerful tool for analyzing ciphers, but we should not forget that it does not prove a cipher to be secure against differential or linear cryptanalysis. And we should always be aware of the implicit assumptions, namely the round independence assumption, and that we are looking at characteristics instead of differentials. Because if we do not take those in mind, bad things can happen, as we have seen in this presentation. And as a last note, I would also like to stress that this is, of course, not implying that this, of course, does not only apply to differential cryptanalysis, but also linear cryptanalysis. Thank you for listening, and I hope you enjoyed the talk.